Hello, this is part 3 in my series on building a digital inventory of Magic: The Gathering cards. In this video, I'll talk about the current process for identifying scanned cards and verifying those identifications. Picking up from the previous video, we have a number of scanned images of cards in our database, but at the moment, these are just images. The computer doesn't know what card they represent, so we can't easily search or sort by card name. At a high level, the basic process is as follows. We download canonical versions of the images of cards from known sources, along with the card names. Then, for each scan, we find which of the canonical images it matches most closely. We identify the scanned image as that card. For demonstration, here is a small subset of those cards, 4 canonical images and 4 scanned images. Now, how do we determine if a scanned image and canonical image match? A first attempt might be to compare the pixel values at each location in both images and computer correlation. I've actually achieved better results, though, by calculating a correlation on the gradients of both images. Now what does this mean, gradient? Well, you can think of an image as a three-dimensional function. X and Y are the X and Y locations of a pixel, and Z is the brightness of that pixel. If you look at an image this way, you get some obvious hills, valleys, and plateaus. At any point in the image, you can figure out its gradient, what direction the slope is in, and its magnitude, how steep it is. Calculating this gradient is actually pretty straightforward. First, using a Sobel kernel, we calculate the X and Y partial derivatives of the image. So, for this X image, each pixel represents how steep the image is along that row. And for this Y image, each pixel represents how steep it is along that column. Black and white represent the extremes of negative and positive slope. So, at each point, you have an X and a Y slope. You can actually kind of think of these as the X and Y components of a vector. And in fact, if you combine them this way, you get a magnitude and angle. For this magnitude image, white represents really steep changes, and black represents pretty shallow changes. So the white actually corresponds to the edges of the image. In the angle image, full black is 0 degrees, and it sweeps around the circle until you get to white, which is 360 degrees. This image is a bit harder to read, so I have this hover over line. As I mouse over the image, it consults the gradient to find the angle of that line, and the magnitude to find the length. So you can see for any location, the line tends to point from dark to light. It points up the slope of the image. Once we calculate the gradient for each canonical image, we can start matching the scanned images. Let's step through that. For each scanned image, we first calculate its gradient, and then we compare it with the gradient of each canonical image. Up here, I print out the correlation coefficient. We pick the canonical image with the highest correlation and name the card that way. So, we name that card correctly, and the next one, and so on. So, that's how cards are identified. In regular use, this debug output is not used, and it churns through much larger batches of both scanned and canonical images pretty quickly. Now, the system isn't 100% accurate, but I want my inventory to be. So, I need a way to check and verify that cards are identified correctly. For that, I have this convenient form. It shows each scanned image, and next to that, the canonical images it was matched to. A human eye can very quickly glance at these cards and tell if they're the same or not. In the relatively rare case that they're not, you just type in the correct name, and the card is fixed. So, this combines the best of both worlds. The human eye is reliable, but slow. So we only use it to very quickly verify, and let the computer handle most of the work. In practice, this computer identification has been about 90% accurate for me. Now that I've built a large corpus of scanned and identified images, though, it's possible to try various machine learning approaches to push this accuracy much higher. Thank you for watching. As always, this code is freely available on GitHub.